at the Portland Quantum Computing Meetup. Let me start sharing my screen here. Okay. Okay. Hi, everyone. I hope you can see my screen. I am Sayonee. I'm a postdoctoral fellow at University of Waterloo and 1QBit. And today I'll be talking about simulation complexity in open quantum systems. So just to make keep things more general, I introduced the word open. So it's not just noise, but you can also have measurements. So okay, let me just remove the screen here. Okay, yeah. So why do we care about simulating many body systems? So anything that human beings or mankind is interested in, be it coming up with designs of energy efficient batteries, or if you are interested in coming up with a really potent drug, if you want to design such a molecule, you would be interested in understanding how many body systems behave. And oftentimes, the quantities we encounter can be properties like conductivity, magnetization, or specific heat. These are some equilibrium properties of your material. Or you can be interested in understanding or studying phases like superconductors or superfluids. Or if you are from the quantum computing community, you can be interested in dynamical properties. So if you want to track a particular quantity, or if you want to track a state as a function of time. So some of these quantities can be hard to simulate by a classical computer, and some of these might not be. So for example, if you have a huge system, and if you want to track the state of the system as a function of time, that might be hard to do classically. For example, if you want to keep track of the exact microstate in model, say the Bose-Hubbard model, or it can be your even spin model like Ising model. So that state can be hard to keep track of in a classical computer. But if you are simulating a macroscopic property, like some expectation values, these do not require the exact description of your state. For example, instead of the state, if you are tracking the magnetization in your Ising model, all you need to do is find the total number of spin up and the total number of spin down. That is enough for calculating your magnetization. You do not need to think about what your spin number 30 or spin number 101 is doing. So quantities like these, we are interested to simulate. And we ask that since it does not require such a detailed description of the state, can it be simulated classically? So there was this really beautiful work done back in 2012 by Jens Seisert and Immanuel Bloch. So they were studying bosons in an optical lattice. So they had a 1D lattice system, and they started with some initial state where every other site is occupied by a boson. And they turned on a Hamiltonian called the Bose-Hubbard Hamiltonian, where you have interactions between the bosons at each site. And these bosons can also hop in between the lattice sites. And then what they did is they tracked the number density at odd sites as a function of time. So what they showed was this. So this plot, so they had multiple results, very insightful results. But for the purpose of this talk and for my own research work, this is the plot that I focus on. So what this shows is on the x-axis you have time, and y-axis is the number density. The blue spheres here are their experimental data. And the solid and the dashed line here are their numerical simulations. And what they did is they changed their parameters in the Hamiltonian. And they showed that for different values and different combinations of these parameters, they found this same feature coming up. That is, their classical simulations were running out of gas after a certain time. It could not replicate what the experiment was doing. So they said that this is an example of quantum simulation that the experiment is doing, that your classical computer could not do. But the question is, their numerical simulation was using DMRG, which is an excellent technique in especially for one-dimensional systems. But the technique calculates density matrix. Now, density matrix is a very detailed description of the state. So it gives you the exact state. But if we are again calculating expectation values, do we need such a detailed information of the state? So this led us to ask this question, or to actually to ask more about this question: how does complexity grow in a many-body system? Or and what kind of complexities or how much of these complexities can be simulated by your classical computer, and for what kind of complexities you need a quantum computer. So to understand this, what we do is we separate out the question of complexity arising from entanglement between sites, or you might call it mode entanglement, or complexity arising from interactions between the particles. So to make things simple, in this talk, I look at this toy model where you have one single site, but you can have any number of particles at that site. And since these are bosons, you're fine. You can have multiple occupations at each site. And we ask how complexity grows in that system if you have interactions. And then we study if you have any kind of imperfections in that site, how does that limit the growth of complexity? So these can be errors or loss. You can have dephasing errors. You can have single particle loss. In real systems, that might come from, say, spontaneous emission or many other sources. And this kind of analysis is true for, in general, open systems. So the only thing that varies is what kind of noise model you want to impose. So to start with, we have this very simple model of a bosonic mode with interactions. And the Hamiltonian here is called Kerr Hamiltonian in quantum optics language. And this is reminiscent of the n-squared type interaction we saw in the Bose-Hubbard model. So you can track the state as a function of time by using the Kerr unitary on some initial state. So your initial state, for us, we took the coherent state because it's the most classical state that you can have. And what we want to see is how that coherent state evolves with time. So to picturize, so the first thing would be is to see phase space representation. So the phase space representation of the density matrix. And this is called the Wigner function or the quasi-probability distribution function. So we know of the probability function, right, in classical physics. So in quantum physics, it's called quasi-probability because you will see some features in this function that does not have a classical description. So to understand how the state is evolving, let's look at this quasi-probability function in phase space. So the leftmost panel shows you the initial state. So you start off from some initial state, which it is a coherent state, and the distribution function is Gaussian. So it's like a spherical blob, and it's completely positive, as shown by this color bar here. And the x-axis and y-axis gives your the coordinates x and p. So these are your conjugate variables. And you start off with some state which has alpha 5. Alpha is nothing but says how many number of particles are there in your initial state. So as you turn on interactions, what happens for short times, this state becomes a bit squeezed. So this is called squeeze state. It's still positive, so it still has a classical description. But if you evolve for longer with interactions, what you will see, this distribution function develops some negative features shown by this red streak. Now, if you evolve for even longer times, you would see that this entire state has spread out and got smeared in your phase space, and you have developed more such negative features. Now, these kind of features, these negative features, does not have any classical description because there is nothing called negative probability in the classical world, right? So this has no meaning as such. And what you will eventually see is after some time, pi, this state develops the maximum amount of negativity and becomes a cat state. So that is the most non-classical state you can have. Now, since we are interested, going back to our initial motivation, we are not just tracking the state here. We are interested in simulating expectation values, right? So we know of this equation. Many of us might have seen it in our quantum mechanics course. This is the equation of motion of an expectation value. It's also called Heisenberg evolution. And H is your Hamiltonian under which you're evolving this quantity A. And if you have an interacting Hamiltonian, what you will see is if you look at single point expectations like A, they will be functions of A square, and A square will be functions of A cubed will be functions of A power 4, and so on and so forth. So what you see here is a hierarchy of coupled differential equations because of interactions. And now, if you want to calculate one such particular moment, you cannot do that unless you truncate it at some level because you have this open hierarchy of equations. So one physical way of looking at this would be, again, going back to the basics, kinetic theory in classical physics. So if you look at Hamiltonian dynamics of n identical particle with interactions, so this is how your Hamiltonian looks like. It's nothing, just you have some kinetic term, you have some potential, on-site potential term, and there is some interaction between the particles. Now, if you want to calculate some expectation value, what you would do is take the probability function, distribution function, and integrate over your phase space. Now, this distribution function is in general difficult to calculate if you have a large number of particles. Now, why is it so? Because if you look at a subset of particles, and if you look at the distribution function of a subset, you would see that it is coupled to the rest of the subsystem via this part or via this integral. So all that it says is the more number of the longer you see in time, you would see that you have to include interactions between particles, and you cannot constrain yourself to only a subset of particles. So you have to include more and more number of particles in defining your probability distribution function. So for example, let's take a very simple one particle distribution function. So then the equation of motion would have this additional part, which is the collision part, due to interactions. If you did not have interactions, you would just get this Poisson bracket. So now how do you want to approximate this collision integral? So that is where the question of complexity lies. So for example, if you say that this single particle distribution function will only depend on two particle distribution function and not further, what you're saying is I will approximate F2 as a product of two single particle distribution function. That is, I'm saying that two particles are uncorrelated. And it turns out to be true for short times. We have oftentimes derived so many equations and relations just by using this condition, where we do not allow enough time where enough number of collisions hasn't yet occurred. Or in quantum information language, you have, or in, let's say, in tensor network language, you might have heard about the term product state. So this is what it means. But suppose you want to evolve for longer times, then you have to include F3 or three particle distribution function, or F4 or four particle distribution function. So this is how you're including the information of how connected these particles are via interactions, and at which level you are going to approximate. Are you going to truncate at the third level or the fourth level, so on and so forth. And of course, you can understand intuitively as you evolve longer with time, lower order approximations are going to fail miserably because interactions have introduced a lot of connections between the particles. And so everything here was in classical. You can also do like a quantum analog of this. Instead of F, you would have your density matrices. And you can also do a similar approximation on how you want to write an n-body density matrix. So we talked about the single mode system. We saw how the distribution function was evolving in the phase space. We saw how those negative features develop. And then we also talked about how the moments were coupled to higher order moments, and we could not solve for one particular moment because of that hierarchy. Now, is there some question?
No, sorry, I think someone just forgot to unmute.
Okay, okay. Yeah, please feel free to stop me anywhere and ask questions if you have. So, okay. So here what we are going to see is now if you have an open system, if you have some errors, if you have some imperfections, then how does that Wigner function evolve in phase space? So the leftmost panel shows your initial state. So let's start from a Wigner function, which has quite a bit of negativity, which does not have any classical description. And let's turn on single particle loss, or let's turn on damping. So what happens is after some time, you see a lot of these negativities, the red fringes have washed out. Even more, the more non-Gaussian states you start off with, the faster the effect of damping or decoherence. So here we see two such examples. The upper panel starts off with a state which has less amount of negativity compared to the lower panel. The lower panel is the cat state. The initial state is a cat state. And we turn on damping. So what happens is after the same amount of time, for the cat state, a lot of these red regions, most of these red regions have washed out. You're left with something completely classical. But here, after the same time, you still have some red regions. So what this says is the more non-Gaussian features your state has, the faster your decoherence is going to act, or the more susceptible, the more prone the state is uh, to be acted upon by decoherence. So let's see if something similar shows up in the moments. So when you look at the equation of motion, there is this additional term that comes due to decoherence or any open system. And this part is called the Lindbladian. So what kind of noise you have, what kind of noise model would depend on the operators you use here. For us, it's just single particle loss. So that's what we are seeing. And what I will not show you the details of the math here, but what happens is because of this additional term, you can see that growth of connectivity between the moments, or in technical language, the growth of cumulants are actually suppressed in open systems. And at very long times, you know that damped systems reach a steady state. And at those times, a lot of these connectivities get washed out. So all these cumulants become zero. So what happens is you can truncate that open set of equations that we saw at some level, and you can just keep track of only a set of equations and not some n or large number of equations. So what I'll show now is this, how does this truncation scheme perform in the presence of decoherence. So by truncation scheme, I mean I truncate that hierarchy of coupled equations using cumulant truncation. And we saw that decoherence gives this additional advantage at intermediate and long times because of suppressed connectivity or cumulant growth. And then what we do is we compare these results with your exact result. So by exact result, I mean if you are solving for the state exactly and you're calculating the moments on that state as a function of time, that gives you the exact result. So again, just to give you an idea, this is just an example. It's a toy model. So I just showed you, I'm showing you only the second order moments here. So the second order moments for this particular model, we call it X, X square rather. So X and P are nothing but, in terms of your second quantized language, it's A plus A dagger, X is A plus A dagger, and P is A minus A dagger by I. So these are your quadratures. And when you perform some experiments, the experiments are going to measure these. So what I show here are two cases. The first case is when your decoherence is high. By high, I mean it's 5 times that of alpha naught, that is your initial state, or the mean value of or alpha naught actually tells you the total number of particles in that state. So for this high level of decoherence, what I show here is even though the state has developed into something non-Gaussian, it's no longer a Gaussian state. By that I mean you still have third order cumulants, or you're still keeping track of your third order let's say your three body density matrix. What this shows is, so this plot actually has three data. So it has the exact results, it has truncation at the third level, and it has truncation at the fourth level. But you don't see any difference because here all of these three overlap. So this truncated scheme, the truncation scheme works pretty well with the exact solution when you have high decoherence. And this inset plot shows you that the cumulants are indeed non-zero. So even if you say that, so what I mean here is, even though I put these cumulants to be zero in the equation, um, the approximation scheme still works very well. And if you lower the decoherence a bit more, so here it's just twice that of your initial state, you still have non-zero cumulants, but what you see is so here you can make out some difference from the exact results with the truncated solutions. But you see that the agreement is pretty good and it agrees for quite a while, even after, so this time scale, this blue line denotes the time after which the state has developed those negative features. Remember, we saw those Wigner functions. And what this shows is that even like if you truncate at third order, that is if you approximate your state to be a Gaussian state, your truncation scheme works again well. You will see some deviations after a certain time. But of course, now you can ask if you lower the decoherence even further. So then what happens? And you might have intuitively kind of understood this. Of course, at some point, this cumulant truncation scheme is going to fail. So what happens is that after a certain point, these third order cumulants become so large that these, when you set them to zero, they introduce quite a lot of error. And after a certain time, these equations, these truncated equations become pretty unstable. So this is when the decoherence strength is as strong as your initial alpha naught that you start off with. So to recap, what I show here is how your truncated solutions agree with exact results. And by truncated solutions, I mean truncation of cumulants. That is, so third order means I'm truncating the third order cumulant. That is saying that, say, x cubed is only a function of x squared and x. It won't depend on x power 4. And truncation at fourth order goes to the next higher order, saying that x power 4 is only a function of third and second order, but will not depend on the fifth order. So this is reminiscent of the hierarchy in the distribution functions that we saw from kinetic theory. So here is an example, where people showed how this truncation scheme worked in a lattice model. So this was a work by Wittot and others in 2011. And they studied, again, the Bose-Hubbard model. And they used this approximation, this exact truncation scheme, And they showed that if you track expectation values like number densities, the higher decoherence strengths you go to, the better the agreement is with the exact result. So this blue line is their exact result, and the red line is the truncated, their truncated scheme. So gamma denotes the your decoherence strength, and they plotted the difference in the number density between two sides. And you can see that as you go to higher gamma values, this agreement is much better. Not only that, they had some additional information as well. So if you look at this color plot, so what this shows is, so x-axis is again time, y-axis shows you the decoherence strength. And the first thing that you see between these two is this nice agreement between the light regions and the dark regions here, which says that the higher number of particles your initial state has, the less is the error in your truncation scheme. And the initial state is a condensate state, or the classical state. So in other words, you can say the more classical your initial state is, the better your agreement is with the exact solution. So another interesting work, which has been in the current literature recently, and you will see a lot of work by different groups in this regard, where they showed in general for open systems like measurements. So measurements can suppress entanglement growth. So up till now, what I showed was mostly related to, well, the last work was not only interactions, they also had a lattice system, and it wasn't, so they did not specify on whether that complexity was from just interaction or entanglement, but it was for a lattice system. And they showed that even in that interacting system, the truncation scheme worked well. But this work talked about entanglement and how in open system, another feature that is a characteristic of quantum systems is entanglement. So what they showed is measurements can suppress entanglement growth. So if you start off from some initial state and you have, let's think about some spin chain or some qubit model, and you have some random unitaries, 2-qubit unitaries, then if you perform some random local Z measurements, what you will see is you can cause a transition from a volume law phase to an area law phase. What this means is volume law is something where entanglement grows very fast, which scales as a volume of the system size. And area law is when the entanglement growth has saturated. So oftentimes you would see strong measurements inducing a quantum Zeno regime, which does not allow any kind of entanglement growth in the system. So to summarize, what I talked about was the growth of complexity can be limited in open quantum systems. And from the simple toy example of the single bosonic mode, what I showed is even if you have non-Gaussian states, that is, if you have non-zero third-order cumulants, your truncated equations or your truncation scheme can work well, pretty well in the presence of strong enough decoherence. And what we are working on right now is to come up with some better representations or truncation schemes on the lattice, something like that I talked about in the previous slides, can further improve on this cumulant truncation scheme. that's all from my side. Thank you. Thanks for your patience, and you can ask me questions.
Sure. So thank you very much, Sayonee. So one question which was raised in the discussion was, how would one directly apply this to quantum computing? Where does this show up when trying to build a quantum computer?
So one important distinguishing feature here is, again, we have to identify what our quantum computer will do. If we want, do we want to get the exact state, or do we want to get some expectation values? So for most part of my talk, I talked about expectation values. And what I showed is there might be better truncation schemes using which you can do a lot of these simulations classically. But not only that, the point of discussion was, well, the point of this talk, and well, my work as well, is to actually identify whether, like, if you have some sort of noise in your system, how much of these simulations actually need a quantum device. So are these simulations, or whatever you are simulating, is it really capturing some quantum feature? Or you can also do it classically if you come up with some efficient representation or efficient approximation scheme. Does that answer the question?
Yeah, I think so. Are there any other questions?
You mentioned open quantum systems. Could you give an example of open quantum system where this can be applied, whether at a microscopic level or a macroscopic level, please?
Yeah, for example, like you can think of, say, in experiments, if you look at, for example, any cold atom systems in optical lattice experiments, you can have different sources of error. So you can have like particle loss, you can have dephasing. So in real systems, there are different sources of error. Or even if you think of spin models or qubit models, where you have dephasing. So these kind of systems, like all that depends, the equation that was showing is you can write that equation for all of these systems. The only thing is, how do you want to model the noise? So that is where you have to tweak a bit. So it's applicable for any open systems.
But can it be, I mean, is it scalable in terms of number of qubits, or can this equation scale when there's a growth of number of qubits, for example, or for example, photons, or any measurement that we're using?
So that's a good question. So so then again, the question is, how do we want to solve this equation? So do we want to solve this equation by calculating the state, the density matrix, or do we want to solve this equation by approximating it? So that is what, that is like you have identified the actual point of research here. So how do you want to approximate the density matrix?
Thing is, I'm trying to lead it back to quantum computing, because I'm just thinking that where in quantum computing this could be used, and I'm trying to formulate that answer, and that's my question essentially.
Yeah. So that's a very good question. So I would say it's like to tell you directly in which hardware and which software and what package we have to use, that needs some more amount of research here, because like as I showed for this very simple example of the single bosonic mode, something like this truncation, like the cumulant truncation, doesn't work below a certain decoherence or below a certain noise level. But we are working on other more sophisticated approximation schemes, which can be scaled to more number of qubits, and we can see some considerable effect there.
Are there any other questions?
Oh, and related to the previous question, another important thing is if you, in one of the earlier slides, I think this one, so you will see this example where this plot, oops, yeah. So this is one example where it shows that the larger system size you have, the better is your agreement of these approximation schemes. And also, like we are seeing in our work, the larger number of particles you start off with, in certain cases, the better, well, the more prominent the effect of noise is. So the faster these quantum effects are going to get washed out. So we are expecting that if we come up with some efficient approximation scheme, it's going to agree even better for large system sizes.
Let me ask you a slightly different question. Say, for example, I mean, you were kind of, because this is essentially a simulation of the noise generated in a quantum system. Now, if you want to control the noise, and using some kind of approximation from a quantum computing, or forget about even quantum computing, from a device point of view, how would you go about doing that? I mean, how would you actually apply these equations onto a model, onto an actual system? I mean, say, for example, you would use some kind of magnetic interference, or what would you be using? I mean, just as a point of discussion.
So I would say the main thing, we are not modeling noise though. It's the other way around. So what we are saying is there is some noise happening. What we are trying to do is we are simulating some observable. So this can be magnetization, this can be your density, number density. We are not exactly modeling the noise. So that is a different kind of analysis. So what we are saying is if you are simulating something, some expectation value, something like number density or magnetization, then how is this noise going to affect that? Does that make things more clear?
Yeah, I'm just trying to get my head around it.
Are there any other questions?
Yeah, hi, this is Alex Khan.
Hi.
So I think that in general, the presentation, from step by step made a lot of sense. I mean, I think you were very clear in explaining some of the, the properties and how you went through them. But I think, I mean, even I'm having a difficult time connecting how does this become relevant for somebody who is getting into quantum computing, or somebody who is potentially maybe used an IBM Q system, and we know that there's errors in the gates.
Mm-hmm.
So I think and I'm sure others might not have this problem, but I think from a business standpoint or from a practitioner standpoint, it would be helpful to understand, is this topic really only connected to someone who is maybe simulating molecules, and at that level there are certain noise and interactions that can be improved by this method? Or is this practical or of some use to somebody who is doing gate operations and using IBM's single qubit system where we do certain rotations to remove errors. So where does this become applicable?
So that's a very good question. So I would say the point of this work was, or the point of my research is actually identifying the simulations that what we are doing with whatever quantum hardwares we have, or even let's say in some physics experiments in some lab. So it's not, the point is not to negate quantum computing. The point is to identify where exactly the power of quantum lies. We are not going to use quantum sources or resources to simulate something that we can do classically. So the point of the research is to identify that boundary and to exactly identify wherein quantum effects introduce complexity in many body systems, which makes them difficult to do in classical computers. And that's why we need quantum computers. So I would say this is more of a bigger question and more in the lines of identifying, like, if you have made some error, how much that error or that noise is going to affect the simulation. So I can put it in in another way by saying, like, so we worry about these noisy systems, right? So if we understand exactly how noise is affecting the simulations, then we are going to understand how much do we want to worry about these noise and worry about correcting these noise. If
So
it's
I mean, this is sounding something like if in fluid mechanics, somebody was looking at the topic of turbulence. Turbulence already is a kind of a noisy kind of a situation. And if you are modeling that, then you have to understand the noise itself. You understand turbulence itself in order to model turbulence or like a fluid with turbulence.
yeah, I mean, yeah, kind of like that. So there was this part in the talk when I talked about this Wigner function, right? So I discussed what the Wigner function is. So it's a probability function. It's a probability distribution function. We know about those. We know about classical probability statistics and everything. But whenever these distribution functions develop some negative regions, it stops to have a classical description. Now, of course, now the state, if we look at the state itself, because it has these negative regions, it stops to have any classical description, and we cannot simulate that state with just by classical means. But if we are talking about some expectation values on that state, we might just ignore that Wigner function and just come up with some approximate classical distribution function that can still give us the exact expectation value, even though I did not include those negative features there. So the point is, if we identify what we are simulating by this quantum device, then we can understand better. So the first step is identifying that what we want to simulate, and the second step is now to like ask, if you have some sort of imperfections in your system, then like how much, like, is there an equivalent classical description of that? If not, then definitely you need a quantum computer, and this system is completely not possible to do classically.
Yeah, I think that makes sense. And I think it's going back to really simulating nature. And, Feynman's comment about simulating nature, you need a quantum computer. And I think just as a clarification, I mean, I'm working in financial portfolio optimization. I've been using D-Wave and to some extent, QAOA. But the question from the business standpoint, or from, when I talk to venture capitalists and other people in finance, they want to know when will they see quantum advantage, or what kind of quantum advantage we're going to see. And just my being in quantum computing now for about 2.5 to almost 3 years, I'm getting more and more of the idea that quantum computers really should be used for simulating nature and not try to take a problem that one does on a spreadsheet and try to, try to simulate that using a quantum computer. So maybe, maybe there needs to be a clarification in the industry of like where are quantum computers really going to have that advantage or benefit.
So I mean, if I could jump in there, I think I would just like to add that regardless of course, what you're describing on the financial side is quantum computing can actually benefit, finance can benefit big time from quantum computing, not only from the cost. If you, for example, look at an optimization problem as a cost problem from that perspective, which is what QWave does very well anyway, but then also from the point of complexity of variables and handling this complexity. Quantum computing today is not ready yet to really add that kind of benchmark. But I think there are times to come when those results will speak for themselves.
Yes, indeed, indeed.
I think there's one more question. I see Shweta has raised her hand. Thank you. Do you have a question?
Hi, yeah, thanks, Mark. Yep. So I thought I came in a little bit late, but so yeah, I think just to kind of address the earlier points of whether it's useful, I think it's like just really crucial. I mean, like the upper bounds of knowing when quantum advantage, or when those points, when quantum hardware would better be used rather than classical hardware. I wasn't able to see the earlier research, but well, there was a journal release, or article released recently by the Wall Street Journal that there were like, Google's quantum computer and Microsoft and different quantum hardwares are coming together to address the problems of ethical or quantum computing scientists and just quantum scientists working in the area are coming together to kind of just understand the ethical bounds as well as the physical and chemical bounds, because without knowing those bounds, there would be a lot of ethical there could even be ethical misunderstanding, or like lack of understanding. So this, I think the point of this research, from what it seems like, is that it helps us quantify or provide a metric as to where when errors occur, how significantly they occur, if that's correct, right?
Yeah.
So,
yeah.
So yeah, if that kind of, I think, is the practical, and also for the use of scientists to improve upon as well. But there's definitely a business like a reason for the business advantage as well, I think. But yeah, I'm mainly just like a student in quantum computing, but I think the business advantage is very much like tied to the work that you did. And I was wondering if the slides were available, but I'm sure like that this was the I
think it's recorded.
Okay, it is. Okay, that works. Alrighty, thank you.
Thanks, Shweta.
Yeah, we are recording this, and I'll post it on YouTube after this, and post the link on the event website.
Thanks.
I see Azeda has a question.
Hi, sorry, I have a question.
Hi.
How do you quantify the entanglements in your setup? Do you use Wooter's concurrence or logarithmic negativity, or you use some other matters for quantifying the entanglements in your setup tanks?
So for my work, I have not. So in this slide, I don't have the entanglement part. I have interaction. So I quantify the complexity by seeing the effect of interactions. The entanglement part came in here when I was talking about a different work, just to show you guys how like complexity growth is limited in open systems. So here they talked about measurements, and they calculate entanglement entropy as a function of time. So for me, I have not yet introduced, or I have not shown entanglement in that cumulant truncation scheme. Does that answer your question?
Yes, thanks.
Thanks for the question.
Yep.
Are there any other questions?
I guess, what do you mean by the truncation scheme?
So the truncation scheme is, so I was talking about these cumulants, right? Or how do you want to approximate, or let's say your density matrix? So do you want to approximate your n-body density matrix as some product of single body density matrix, or some products of two-body density matrix, or three-body density matrix, or so on and so forth? And that boils down to the question of these coupled equations that I was showing, because you have interactions, you have like your equations of motion of any particular moment or expectation value. It's coupled to other like higher order moments. So here you have like an open set of equations. So you cannot like pick one of them at random and solve. So you have these couple differential equations, and you have to truncate at some order. You have to say, okay, I'm not going to bother about anything greater than x cube. I will just only keep track of x cube, and that will be enough to keep track of any moment. So that's the truncation I was talking about.
Okay, that makes sense. So it's kind of like if within many differentials kind of, oh, okay, that makes sense. Yep.
Mhm.
Super. So maybe we can thank Shani again, and thank you everyone for joining. And yeah, I'll post the video on YouTube this evening.
Thanks, Mark. Thanks for inviting me. And thanks, everyone.
Thank you.
Bye.
Thank you, everyone. Bye.
Thank you. Bye-bye.